questions, and since Dr. Masani is the external examiner, I'd like to start with him, but maybe we can move Dr. Kushki in a bit closer so she can hear as well.
Okay.
We'll have to find an optimal location for that optimal alignment. Okay, so we'll start with Dr. Masani.
Yep. So the thesis is very well written. I think it's and also the study itself is a good job. I think you did a good job, and especially considering that you are in a clinical engineering program, which you have only limited time for research. So I think it's a great achievement. I have not many questions, but I have some questions actually about the ASPL mechanism. At first, I just want to confirm several things. So the ASPL is that locking system, automatic locking system. That's the kind of uniqueness of your system, and no other commercial device is having that, right? No other commercial processor.
Yeah.
So this is a unique.
Yes.
Okay. And I'm a bit confused about the instability zone. What actually means zone of instability?
Okay, so the zone instability is, it allowed me to show.
Sure. I understand how it's defined, but the meaning of that, it doesn't mean that, for example, the center of pressure is within that area, which determines the engaging and the disengaging. That's not right.
Yeah, so how the ASPL mechanism works is based on the load line on the forefoot. On the foot, it's based on the load line, the ground reaction force factor.
Yeah.
So the zone instability indicate that for any load line to pass through the zone instability, which is in front of the control axis right here. So in this case, when the load line is in this zone, it would actually pass through it would actually go in front of the control axis, in which it would create an extension moment. So that would allowing the V to get locked.
Load line, you mean the force vector?
Yeah, the ground reaction.
But in other places, you said that the force vector passes the behind of the control axis, then the lock disengage, right? Is that correct?
No, I'm sorry, did I correct it? It's if the force factor is behind the control axis, in this case, it would actually create a flexion moment in this case, so it actually pushes the lock to be engaged.
Oh, okay, so they maybe the opposite way. So that vector is in front of the control axis, then the
lock will
disengage.
Yes, and then.
But that is that always happening that the end point of the vector, which is center of pressure, is within that zone of instability? Is that always happening?
Yeah, you could compare the zone, the center of pressure, something straight here, it also will happen.
So if the center of pressure move to, which is for, this way, left side, then that means that force vector will move to this side of the control axis. Is that correct?
Yeah, so for the axis alignment, the ASPL mechanism to work, the patient actually needs to have a pronounced heel strike and also at the toe off. So that's how to control the ASPL mechanism. Right. So for a patient with like a stiff gait where she cannot they have to keep the skate and where she cannot roll her foot to the front or so to shift the force factor, to shift the ground reaction force factor to the front, then you would not be able to unlock the ASPL mechanism, because that's one of the design features where the knee will remain extended to provide the stent face stability, to provide the stent face.
So when center of pressure is within the zone of instability, the system is locked, engaged, and then when the center of pressure moves this side of the zone of instability, the lock disengage.
Yeah, it is here, it will disengage. It is here, then it will not disengage. So to heel strike, it will remain extended, but then toe off, it will can initiate the locking. So this is one of the reasons why is because there's a lock spring. A lock spring in here. So in which the lock spring is constantly applying a force on the lock. So constantly applying a force, so we would keep the lock from being locked. So that when the force factor is in your front, and the moment is greater than the force on the lock spring, then you can actually push the lock back, allowing the knee to flex to open.
So can you go back to the? So in case of the center of pressure is here, and the force factor is like this, what's happening?
The force factor is like this.
Yeah.
So in this case, the lock.
So my question is, if the lock are not happening when COP is in this area, or the force vector line is front or back side of this control axis, what is the key?
The keys actually have also the key was actually have the force factor and also have the moment that would be greater than the lock spring.
Oh, right, yeah. That's
so the lock spring will constantly keep it from locking. So that's one of the features.
Okay.
That's why it's the zone instability. So even though like the force factor may be in the zone instability, that's not necessarily means that the lock will be unlocked because there's a lock spring.
But in terms of the location of the force vector and the system, the zone of stability is kind of key, not the force vector line and control axis. Zone of instability and the spatial relations between the zone of instability and center of pressure is a kind of key. Is that correct?
Sorry, can you repeat that?
So I understand that the lock spring is one factor to determine the engage and the disengage. But at the same time, the spatial relations between the center of pressure and the zone of instability is a key factor to determine the engage disengage.
Yes.
Is that correct?
The zone instability.
Thank you. And so in tuning that alignment line, I think you decided to use like a 5 degree.
The 5 degree, yes.
5 degree,
yeah,
right?
Yeah.
Where that 5 degree come from? I didn't.
Oh, sorry. This. So what happened was I have used different knee shank foot models. So basically, I have created a simple knee model, a simple shank model and foot model, so we compare it and put them together. And those are using the anthropometric data for children. So since we want to design the knee for a wide range of children, which is 6 years old to 12 years old, that's why we're using different data for that range. So how that 5 degrees come is when we were using the AT, try to look at the established X alignment on the AT knee, and look at where the zonal instability is going to project on the forefoot for all those ages. We noticed that for adult we actually achieved 55.8% for the zonal instability, but then for 6 from 5 years old, only had 45%, and also for the other age, it's not close to anywhere that we want. So therefore, but then if you can see the data as the age decreases, the alignment on the 18E on the foot is actually getting smaller. So how we arrive to the 5 degrees is when we are trying to, because we want to try to establish a similar zone instability for across all ages. So when we're looking at 5 degrees, we're able to provide a similar number across all ages, and that's why we picked the 5 degrees in certain.
So simply from the size of the book, but to get the 55%, use the 5 degree.
Yeah. So for the pediatric, we use
for a child's body. Okay. So But that's the thing that you did to decide the alignment line. So you didn't. I would think that because the alignment line is kind of key to have a smooth locking, right? So I would think you could do some simulation or something using a simulating gait, child's gait, to decide the alignment line. So did you consider something like that, or like after seeing that gait data, you would be able to tune it again, right? Based on the sound rings data or something.
So yeah, based on that, and then first we did not, like you mentioned, using the simulation. We did not, in the beginning of the design process, I did not consider that because when the design decisions that I made is that the ATD is the proven technology. So therefore, and since there's no data on what the optimal alignment would be, so therefore I just want to take the F alignment on the ATD and then put it on the pediatric knee, and you see if that alignment would actually, and then adjust it so that you see that if that alignment would be optimal for the pediatric user. So now, since seeing the data showing that the participant saying that she has a little bit harder time on initiating swing phase compared to the conventional knee, which means that maybe the alignment needs to be adjusted again, so in order to establish a better results on the initiating swing.
So you basically scale down the size to fit that child's body only size, but probably the gait is not just scaling down one. That's why there's such a discrepancy happening.
That's right. That's it.
Yeah. So this mechanism is very interesting for me, but do you know if that similar thing is happening in actual human walking? Because in human walking or standing, I know that we are locking a knee somewhat, and at a certain point it flex, suddenly flex, right? So do you know if it's the same thing, like a gravity vector and force vector and some spatial relationship between the gravity vector and some point, like a control axis, some point, certain point below the knee is determining the locking mechanism or not. Is this happening in the physiological control system too, or?
No, in terms of the stand face flexion, it's usually not happening in the prosthetic gait. It's because we want the prosthetic to be able to extend the position. So normally throughout a lot of the knee is actually just having a zero stand face flexion. But that will be something to look into, since maybe we can incorporate like different mechanisms to allow the stand face flexion to absorb the shock or something. But
sorry, my question is, if you know if that is happening in normal gait or not.
Normal gait.
Yeah, in normal gait we lock knee somewhat. Of course, it's not a complete mechanical knee locking, but our knee is somewhat locked. And suddenly it starts flexing in a certain point of gait cycle. I just wonder if that flexion point is happening in similar mechanism, like a similar criterion, like similar determinants, like the spatial relationship in the actual force vector and a certain point of the just single point below the knee is determining such flexion point or not. So simply my question is if similar things happening in physiological control system or not. Do you know about that?
Oh, similar things happen.
Yeah, in the normal gait or not.
I would think the similar thing would happen because that's why we try to we want to design the knee to try to better simulate the able body gait, but due to the limitation, right now we were not able to see the data. It's really close, but not like exactly the same. But similar thing does happen. Indeed, when you're talking about the unlocking a knee or doing the swing phase and things like that.
Did you check the literature about normal gait locking mechanism, locking a knee in normal gait?
Well, I did not specifically check the locking.
Okay, thanks. So, yeah, I also have interest in that user's feeling about the locking mechanism. So I would think that such relationship, spatial relationship between the of instability zone on the center of pressure or force vector and control axis. That kind of thing can be kind of different among some people. So depending on the gait. So I would think it's that the alignment line it's better to be adjustable for a person and customized. Is there any potential to have it like an adjustable mechanism, like changing the location of the control axis or something?
So far, did you just look at the axis alignment on the knee? I do not think that there will be potential changing just the axis alignment on the knee. But then that problem can actually also be addressed in the overall prosthesis alignment, in which maybe we can move the knee posteriorly, anteriorly in terms of how much use of an inching swing face the patient wanted, and also we can rotate it. So that would also help aligning the knee as well.
Thank you.
Thank you. Dr. Kushki, did you have questions now?
Sure. So I think maybe I'll just focus on the cervical subject study and the analysis and interpretation of the results.
Okay, I'm going to move you a little bit closer to me.
Okay, great. So I just want to start with something that we discussed last time in terms of the standard deviation. There are a few places, for example, where you talk about the spatial temporal results, kinematic and kinetic variables, where you just kind of compare the numbers and you say, oh, it looks like they're the same, but they're not the same. And I was wondering if you used any kind of specific criterion or statistical test, or you're just kind of saying how different they are.
Oh, so you're saying for the spatial temporal parameters, I say they're the same, but they're not the same? For all
for example, you say on page 58 that the smaller PCI, that the conventional knee has a smaller PCI variable. So in your thesis, you don't actually have the standard deviations, but in the slides, you provided the standard deviations, and it looks like the value is actually within one standard deviation of the typically developing population. So probably it's not statistically different. So I was just wondering if you could think about a way to compare these numbers statistically.
Yeah, it's because we only have conducted 3 trials to do that. That's why, and there's only one participant. That's why we did not do any statistical tests. But yes, after.
But you can still compare that one value to the distribution for the typically developing population, right? Because you have to meet a standard deviation for that.
Yes. That's why in the revision of the thesis, I started to try to incorporate all the standard deviations. So in the PowerPoint, I've incorporated some of them, which is the PCI value as well as all the gait data, and compared to the able body, and we try to see if it is like beyond the standard deviations or within it. So in this case, we can still have a general indication of whether the data that we have is good or bad compared to the able body individual.
So the PCI value is actually within one standard deviation.
Yeah. So.
I mean, you talk about how they're different in your thesis, but you may want to revise.
Yes.
That makes sense.
Because in my PowerPoint I've stated that, I'm so apologize, I didn't write in the thesis. Stated that even though the PCI value it's higher, so it's indicated as a higher energy expenditure, but then since it's still relatively close to the able-bodied individual, which indicate that the pediatric knee may not actually cost a lot more energy expenditure, in which we will know more if we have a 3 weeks acclimatization period to allow the user to actually adapt to the knee. So then we can actually truly to see how efficient the gait is. But now, since looking at just the initial data, we can know that there's a potential for the pediatric knee to provide an efficient gait.
Okay, so my point is, if something is not significantly different statistically, then you don't say it's higher. Because it's still within the variability, right?
Yes.
So it's actually better for your results. Probably too. So it was interesting that the participants all the other results that you have
Mm-hmm.
in terms of the spatial temporal parameters, the kinetics, all of that.
Mm-hmm. So I think one of the reasons for the higher fatigue 3 out of 5 is maybe due to the fact that related to the extension cyst. As mentioned in the gait, the participant actually exhibits some of the asymmetry pattern, so in which she actually have to put more effort on the sound limb in order to allow the swing face to swing through. In that case, she actually need to since she has to provide more effort in the sound side to stabilize herself, allowing the prosthetic limb to swing through. So that may also contribute to the energy expenditure. That she feel more tired when she's walking for a long time. At the same time, she also mentioned that in compared to the conventional knee, in which in this case she actually need to have place her foot closer to the toe area in order to initiate swing face. So that because she was telling me that she has to concentrate on her walking, so that may also contribute to the increased energy expenditure, or she feel more fatigued because it's a little bit harder to initiate swing face when she was wearing the paediatric knee. So it's the step face and swing face.
Okay, great. So you mentioned the toe issue. Is that also something that came up with the AT knee, or is this new to your design?
Mm-hmm. I do not think there's something happening in AT knee, because AT knee is pretty well established and they have its optimal alignment. So, and then but for us, we do not know what the optimal alignment for the overall thesis would be, first of all. At the same time, we do not know, we try to investigate if this axis alignment on the knee was actually good, optimal for the pediatric user. So therefore, just looking at this study, maybe we have to revisit the axis alignment in the knee, and also try to establish what would the optimal overall thesis alignment would be. So that may actually help to have an easier time to initiate swing face, and therefore reducing the energy expenditure.
Okay, great. My next question is about table 5.2, which is the results of the 6-minute walk test for the able-bodied children.
Mm-hmm.
Why is the resting heart rate so different between your participants and their results?
In this, I do not know, but I apologize. Did I incorporate did I include the standard deviation in the 6-minute walk test in that table?
No, there are no standard deviations in your thesis.
Oh, I apologize for that. Yeah, so I actually added that. So the difference is actually, it's also, like you said before, it's within one standard deviation. So the difference is, this is just the variability. I apologize for that.
But there's a 30 beats per minute difference in the resting heart rate. That's probably more than just typical variability in heart rate. So do you know if it's the same age? Are the participant groups the same age, or gender, or are there any other demographic variables that are different?
Oh, so for the data that I took from the literature review is actually on the pediatric population, which is from 5 years old to 18 years old. So that might go from 5 years old to 16 years old. So that may actually also contribute to the huge variability, because that study have been done in collecting data from over 200 participants, and to see if they to look at their like 40. Sorry, I don't know the exact number, but it was like in the already 50 or 100 participants, in which is trying to establish what would be the reference value for the 6-minute walk test would be. So I was comparing that to compare my participant to that population. So maybe that will introduce more variability because of the age difference.
Okay, so it would just be nice to, if you could report Ngan for the demographic variables for those other studies as well.
Yes, definitely.
Sorry, trying to get my notes organized. So again, in chapter 5, the few versus what you say, there are no significant differences. You can't say if there's a significant difference unless you do statistics about that. So the extension is this. It says that there may be issues with the torque, with the amount of force that's provided. So we're back to your slides. I think it was slide 19 and 20. You actually calculated adjusted your parameters so that you get 50% of the torque generated in the ATP. So do you think that you should have done more torque there? And if so, what would you have to do differently in your analysis here on page 519?
So what would I have to do to increase the extension assist torque?
So the analysis that you have, you had come up with this number, 60% of the torque generated in the AT, and that was your target. So clearly that target wasn't enough.
Yeah.
So my question is, what could you have done differently to get a different torque that would have been higher that would actually practice be sufficient?
Also so how would I establish the number that we want for sufficient extension assist?
Yes.
Okay. I think it depends on I would look at it in two ways. First, I will look at data and see what are the differences between the conventional knee as well as the pediatric knee. I want to look at the differences between it. So in this case, and then also if the difference, and based on that, and also look at the extension assist on the conventional knee to look at what are the spring rate on that knee would be, and then doing all of that. So using those to consider how much I have to increase the spring, the percentage of torque I want to provide it by. So that will how I gauge it. At the same time, I also will have I will pick out different spring and different spring rate. In this case, and when the participant was actually testing the knee, so I will be able to swap in a different spring to see which one she'll feel comfortable walking with it. So it'll be two ways. So one will be look at the user feedback as well as looking at the comparison between the conventional knee as well as my design.
Okay, great. So I think those are all my questions.
Thank you so much. Thank you.
Okay, that's great. Thanks, Dr. Krishnan. So I'm going to ask a few questions now. So I want to go back to the beginning when you first started to think about the design criteria. So you started with the 18 knee, and you wanted to be able to downsize it. So do you want to walk us through the decision-making around some of the design decisions that you made in terms of what the new design needed to address?
So that when we start with the physical specification, so we listed that the knee should not exceed 500 grams and also no longer 150 millimeters. And this number has actually come from when we're looking at the commercially available product, we were looking at their overall dimensions and length as well. So how we come up with this number is by looking at it and also looking at how much, what are the normal size of those knee would be, and that's kind of set as constraint. But then this constraint is actually a little bit loose, where we have 500 grams and 150 millimeters. It's actually a little bit on the heavier side compared to the commercially available knee, as well as the longer. And this is because since we're doing this pilot study, this pilot design, we do not know what would the constraints for implementing the automatic lock mechanism. And there's too many uncertainties as in how we would be able to incorporate the extensions and things like that. So therefore, in this study, we want to prove that this mechanism can be applied to the pediatric population, and we can use it to produce a knee. So that's why when we're setting the weight and the length restriction, we do not have a very, very strict straight weight and length restrictions, because the main goal of the study is to demonstrate that this knee, the ASPL mechanism can be produced in pediatric knee and can be used by the pediatric user. So now, since that we prove that the technology can be used, is applicable for the populations, then we proceed to try to optimize it, to make it smaller, to make it lighter, so that we can have, so the number will be comparable to the commercially available product, in which they have the same criteria, as in they have 60 kilogram weight capacity, or they are able to incorporate the stamping control and extension the extension assist and damping control. So we'll compare it to that as well. And for the 140 degrees knee flexion, it's also based on the commercially available products. They offer the range from 130 to 160. But for the 160 degrees, those are the the polycentric knee, and that is actually the polycentric knee, and those knee is actually known to be able to provide a greater knee flexion angle. So we pick 140 degrees just because it's kind of like the median range, the median value between all those products. So we think that if we can achieve at least 140 degrees, it will be adequate. And for weight capacity, 60 kilograms, it's just the knee is 45, and then we try to for 60. As for the stand face control and swing face control, like I said before, the objective for this project is to incorporate the ASPL mechanism. And then in order to do the ASPL mechanism, we have to establish the X alignment for pediatric users because we want the knee to be able to be used by the pediatric population. And we wanted to incorporate the swing face and extension assist and the denting control because that's where the other products, commercial products, the majority of them lack. And because we try to aim to provide a better swing face. And for flexion stop, it's just to protect the extension assist. Because if the flexion stop is not implemented into the design, and when the patient is flexing the knee, their socket might potentially hit the extension assist at the back, so that might just damage it and might cause the failure of the knee. So that's why we want to implement. So this is how I list out all the design criteria.
I think elucidating some of those decisions would be really helpful, I think, in your thesis. But I'm just wondering about whether there are some other things that you should be thinking about. I know in retrospect now, you can't go back, but just in terms of future recommendations, thinking about it from a user's perspective. So what are the things that are particularly important from a child's perspective that would be important to be able to integrate into a new design for the knee, for instance? And the reason I'm bringing that up is that one of the things that the participant that you had in the study said that she liked about the knee that she tried was that it had a versatility that could be used for different purposes. It could be swimming, running, and for different types of activities, but it's not on the design criteria related to that. You think that would be an important aspect to include. And I also noticed in reading the thesis too, there was a lot of give and take in terms of which is the criterion that you want to be able to adjust in order to be able to accommodate this. So you made some judgments in terms of what was important, but to what extent did that have an impact on the user's perception of that change, and is it significant? So a lot of the decisions that were made it seemed somewhat arbitrary. Like you may have run into a problem, maybe there was an issue with the noise. You mentioned that when I think it might have been the second trial where you were testing and you noticed that it was a bit noisy because of there was some spring noise, and you said, well, maybe we can just lubricate that and eliminate the noise. But the question is, from a practicality side, would you be expecting that after the child's gone swimming, they're going to be re-lubricating it again just to eliminate the noise? Or do they want something that's maintenance-free? And where is that in terms of the hierarchy, in terms of importance? And also just related to the weight. One of the recommendations you had was around changing from an aluminum base to Zytol base, which you might be shaving. I don't know how much you're going to shave in terms of the overall weight, but is that something that's important to the user? I mean, do you need to consider what the cost is to the individual user? Maybe it's more important to be able to stick with aluminum and then live with the fact that it's a bit heavier, because maybe perceptually there's no difference in terms of that. So again, to this, the user significance of some of the design decisions. If you want to weigh in on some of that, what do you think?
Yeah. So in terms of if we talk about some of the design decisions, this kind of give or take. Yes, because this is a pilot study, and then we did that. So there are a lot of design decisions where we do not know we do not have any reference. So, but then I think that is very important to incorporate. So that now we have done the study, I think that it's very important to incorporate all the user feedback that we have from the user, and then in order to incorporate all the features in it, such as can we make the knee lighter, or can we actually make the knee lighter, or can we have it change the X alignment so that it initiates swing base more, so that she can participate in more activities like running, like she said she was running, or playing dodgeball. And I think those are very important. And in terms of the sorry, what was in terms of the maintenance, that will be a very, very important priority. So since this is a pilot design and we do not foresee that the shaft and the material that we use for the extension assist will actually making noise, we do not foresee that because there's the same material being used in the 18E. So since now we notice that, oh, if the participants walking with it, they're making a squeaking sound, then maybe we have to revisit what the different materials that we can try in order to minimize all those effects, so that we can try to make the knee as maintenance free as possible. But by doing this study, we'll be able to find out all those areas of concern, and then in the renewed design, in the updated design, then we can address all those problems to do it one step at a time. So this is a pilot study, a pilot design. We need different iteration in order to keep improving it to produce the best product that we can do.
We could move on to just some of the decision making around the selection of the measures that you were looking at. So you did talk about the 6-minute walk test and decided to choose that. Why the 6-minute walk test? What was so significant about that?
So 6-minute walk test, I use it to measure the energy expenditure, but the gold standard in the clinical field is actually to measure the oxygen uptake and things like that. But then since to measure all that, you need a very expensive equipment, and also you need all those resources that we don't have. So therefore, we decided to use the 6-minute walk test to measure this energy expenditure, because it shows that there is a good correlation about the 6-minute walk distance and the peak oxygen uptake. And a lot of studies have shown that the 6-minute walk test actually have a high reproducibility, and also it's very reliable in terms of determining the energy expenditure. So therefore, we decided to go with the 6-minute walk test.
So can you tell me a bit about its reliability and validity for pediatric population?
For pediatric populations? The study has shown that for when we were trying to, the study is that we have to invite a bunch of school kids, normal age children, school kids, and then ask them to walk in a self-selected walking speed in 6 minutes. And it shows that for in terms of the PCI value and things like that, this actually is and then the oxygen uptakes have a really good correlation on it. So the higher oxygen uptake indicate that they actually have a further walking distance than 6 minutes. And then at the same time, it also shows that the PCI value is pretty consistent, and that's why I think that it would be a good measurement tool.
So do you know a bit about its reliability in terms of, and this might have, help to answer Dr. Kushki's question around the variation in terms of some of the values that are seen between the pediatric prototype as compared to the typically developing population. So we're looking at resting heart rate, but we want to talk about the 6-minute walk test in particular. Give a sense of what the test-retest reliability is of the measure, the extent to which it's reproducible between sessions.
Yes. Sorry, on top of my head, I do not remember. But I found the decision is because I found several papers also suggesting that reproducing, and that's why I made the decision. But right on top of my head, I do not remember.
Yeah, I think it's important to include some information around the measurement properties, just so it, reliability sets an upper limit on validity for one thing. So if you have a measure that may be used by a lot of different groups that don't really look at its core measurement properties, it just leaves you to question what the results are that you have. So it's important. It might be very reliable, but you just need to be able to say that. It's like reference paper.
Yes.
And it's really related to the way in which it's used too. So if you're referring to an adult study and you're citing reliability of that, it's better to make it close to what the population is that you're using it for. So if you don't have that information, then you just need to be able to say what the limitations were in using that particular measure. And then in terms of its validity, so the 6-minute walk test, although it's used for typically developing kids, what about in the amputee population has been used?
Studies have used it in terms of the pediatric populations on the amputees population, as well as different clinical conditions such as for stroke patients or for cerebral palsy patients. So this tool is actually widely used in different view. So definitely including the amputees population.
Great. So I think not just the six-minute walk test, that was just an example I picked, but the other measures that you're using as well. So you're using that as a way to be able to make some comparisons within your study. You just need to have that piece in place to be able to provide some context for decision making about the differences that you saw. And there may even be some of the more established measures give you an idea about what the minimum detectable difference is too. So it weaves in the reliability piece and gives you a sense of the difference that you're seeing is actually something that's beyond measurement error. So that would be important to be able to know. But similarly with the questionnaire that was used for acquiring the child's perspectives too, there wasn't a lot of information around that. I know where it came from, but it just wasn't articulated in the thesis. I think you need to be able to say that it was taken from an adult study, it had been used or been used in a few different studies, saying what those are and how you adapted it for children, because I think it was used for adults. And some of the decision making around that would be helpful. There was just a small point around I can't let it go because I think it's important to change, because it speaks to just the research ethics side of things, and that's just the way in which the child was recruited for the study is different than what you actually responded to the RDB around too. So there may have been a disconnect in how it was written, but if you just look to see how you responded in terms of how that child was going to be recruited, and then actually what happened. Just because it's inconsistent.
Yes.
Okay. You mentioned that, and you recommended that you would see that it'd be important to be able to do a study with many kids, and that way, come up with a little bit more definitive conclusions in terms of the performance of the knee. So if you had to design a randomized controlled trial, what would be your primary outcome measure? What would you decide? Normally you make a decision when you're powering a study, what's your primary outcome, and then you have a series of secondary outcomes. What would you choose among all the things that you were looking at as your primary outcome measure and justify?
I guess my primary outcome within this case was actually try to compare how much the prosthetic knee was actually helping the user in terms of how much load is being reduced, in terms of how much work she has to do or he has to do with on the sound side, because that's one of the measure outcomes when you're comparing with the knee, is to see if the knee is actually helping improving the gait functions of the user. If the participant by using this knee is actually need to have more effort on the sound side, so that means that there's kind of indication that the knee is not functioning very well. So that if I have a randomized trial, and I will actually randomized trial, and if I have different children, then I will actually test out to see how different knees have different effects on their sound side, and compare that, and that's also that will be my primary evaluation if I have more kids and more different types of knee that I can test.
Do you have a measure in mind that you might use for that?
So the first couple of things, I would also look at the kinematics and kinetics on the sound side, and also compare that, and then look at see if there is any asymmetric pattern that we've shown. If it shows that there's very symmetrical, and also that's showing that the work on both sides is pretty even, then that's kind of one of the things I would want to look at. And also we definitely compare the value to the able-bodied children. You see how far off and how closely matched the value would be. So that would also be an indicator of how can we improve the gait function of the user by designing a knee.
So I'm glad you brought that up, because I was going to ask a question relating to that too. So there's a bit of a movement in some areas of rehabilitation around comparisons. I mean, there's studies that look at participation of children that have disabilities versus kids that don't have disabilities. But there's an argument that we shouldn't really be comparing to a normative population, because participation isn't something that's, it's governed by a number of other factors as well too. I'm just wondering what your thoughts might be around the validity of and maybe moving towards the gold standard and comparing against an able-bodied population, is that really the ultimate goal of creating a prosthetic system, so that, you know, there's the knee, there's all the other components, including the foot. So is the idea to create the average gait and you know, not be satisfied with the commercial systems that are available until you reach that, you know, the ultimate goal of creating gait that's perfectly normal, average? What do you think about that?
In my opinion, I think for kids, yes, I would strive to try to improve the gait as much as possible, try to get to the level as close to the able-bodied children level as possible. It's because for example, the participant that I have in the study, she's actually very active, and she was involved in the hockey team and also playing dodgeball, like I said, dodgeball team with her friends. So I think that to be able to provide her with a good prosthetic knee where she can move freely and move efficiently, and allow her to participate in different activities, not only improve her physical level, but also improve her social life. So therefore, I think that's very important to keep improving the knee, to improving the gait, up to the able-bodied level. It's not just because the physical, but also the social, and maybe also her development.
So I'm kind of going beyond what you'd be expected to talk about in your thesis, but I think it's worth thinking about too. So maybe I'll pass on to Dr. Anderson.
I'm actually going to follow up on that. I mean, I think when Corinne asked you about the primary measure, you talked about a very sort of biomechanical outcome measure you would use in terms of the loading of the sound leg. But then I think as the question was evolved a little bit further, what do you think is really important to the child? You started talking more about her ability to use this essentially as a tool to be able to participate and do other sporting activities. So those two things seem quite different to me in terms of what the child seems to be important to the child, and you know what's essentially what outcome measure you would select to measure. So can you just elaborate on that a little bit more?
Yes. So I think they actually goes hand in hand. If we can improve the biomechanics of the knee, then we'll be able to improve her ability to do different activities. It's because in one of the paper I've read, it's shown that once the participant, the individual have the amputation, then it actually affected her social aspect, in which her activities have changed between before the amputation, after amputation, because the loss of limb, loss of function. So they were instead of being able to go outside and play, they say that those pediatric groups actually just rather stay at home and watch TV or things like that. So therefore, I think it kind of goes hand in hand. If I be able to increase the biomechanics of the knee, of the gait, and therefore I think that it will be able to increase their likelihood of doing social activities. And of course, right now, so far, I do not have a paper to support that, and it's just a theory that I have. But if we were actually to investigate that, then we actually would look into more study and see what is the relationship between the social group, the social activities, or the social level in comparison to the mobility of the patient. And we would look into that if we were to investigate that.
Right. So I think I like your last answer. I think we don't know. We don't really the answer what biomechanical changes really have an impact on the person's function, and that there is not a lot of literature. And I think before sort of saying yes, this is my primary measure, I think what would be a good idea is just to go back and try to find what is available and try to make fixes. I guess one question relates to your modeling of the axis alignment, where you from a theoretical point of view determined what you thought would be the optimal zone of instability. And as you went on to test, you found out that maybe there was something off, right, in terms of that. Can you, how would you go about and to determine in the end was this discrepancy due to the issues with the model, or because you also discussed the overall prosthetic alignment, was it perhaps associated with that? Can you speak to that a little bit?
So I think how would I go about it is first we want to eliminate one thing at a time. So maybe first I will look at the overall prosthesis alignment, because since we're the prototype already, so maybe we can do more testing and testing out different alignment and see if the patient, the data, the kinetic data have improved, and also the perception of the user have improved. And if we do different changes and then she still think that the conventional knee is actually can allow her to have an easier time initiating swing phase, then we will look into the axis alignment of the knee. So first I will address try to look at the overall prosthesis alignment, since the prototype's already been made. So, and after that I'll look into the actual axis alignment to see if that will be able to change that.
Okay, so my question is why didn't you actually take the child's prosthesis and compare it back to your model to see whether there's just differences in the alignment, or whether, where potential sources of error or difference to it?
Yes, that will be a great point. That will be a great starting point to do that. I guess in this case I didn't do that because I do not have the prosthesis. But if I were to try to for future work to improve the axis alignment, that would be the things I would need to look at.
But we do have access to the prosthesis.
But she be wearing it. That's
right. But she's been here a couple times.
Yes.
Okay, so I would definitely put that as something for future work, perhaps.
Yes.
A way to start to validate the model and start to understand how, whether we need to start tweaking the axis alignment, or whether perhaps it has something more to do with the overall prosthetic alignment.
Yes.
Okay. What were the instructions that you gave for the 6-minute walk test?
For a 6-minute walk test, I asked the participant to walk and self-select the speed, but then try to cover the distance, as much distance as possible. But I just asked her to walk and self-select the speed, because I was following one of the standards that I found online on one of the American Heart Association. So I was trying to follow the instruction doing it, in which they're saying try to encourage the person to walk in walking speed, also to walk and to cover as much distance as possible. So that's what the instructions I gave her, to walk, self-select the walking speed, walk at constant speed. If you're tired, you can rest. There's no problem until you are recovered, and you can keep walking. So that was the instruction that was given at the
So they seem a little contradicting of each other. To the walk itself, select the walking speed, which is typically sort of seen as your normal walking speed, and asking them to cover as much distance as possible, which one would actually walk at faster walking speed.
Sorry, I asked her to walk at self-selected walking speed, and then she can keep walking until she can cover as much distance. Because I mentioned if she's tired, she can stop, no problem. But just that she can just keep walking. Don't stop just because that's what I meant by cover as much distance.
Okay, so at once walking speed, you can only cover so much distance within 6 minutes, right? So the instruction, the important instruction is, I guess, how fast do you want them to instruct them to walk. So I think the correct instructions are, and don't quote me on this, but I think the instruction is to ask the person to cover as much distance in 6 minutes as they can without running, something along those lines, which typically would encourage the participant to walk at a faster speed than what would be self-selected.
Yeah, see that, because actually I was just reading that protocol again. There is some study was encouraging the participant to walk as fast as possible, and then this, for some of the 6-minute walk, that was actually encouraging the participant to walk at a self-selected walking speed. In this case, I was following this protocol, so that's why I was asking the participant to walk at a self-selected walking speed.
Okay. All right, so just maybe add those clarifications and make sure we have the right references that do specify that.
Yes.
And just a quick note, from Masani's question about the instability alignment, can you go back to that diagram where we had that? can you just quickly go over how that zone of instability, how those lines are actually determined?
Oh, the line is determined. So first of all, I establish a line from the toe, going through the control axis, and also another line is going from here, going through the knee pivoting axis. And the last line that I did was, and then so that would actually create one zone, and then this would create another zone, and then also the third line would be from the knee, the control axis to the pivot to the from the pivot axis to the control axis, and projected to the projected onto the foot. And those three was actually create an area, and when you superimpose them, so the overlapping area will be representing the zone of instability.
Okay. So to then achieve knee unlocking or the instability, what needs to happen at both of those axes?
What needs to happen in both of those axes?
Yeah.
So first,
in terms of the moments.
in terms of the moment. So so I think what has to won't happen on the is that the force vector actually has to be in front of the control axis, in which it would create a flexion, so it opens up, and so for the top one, I am not quite exactly sure.
Well,
But I think that if the force factor is located in front, since zone of instability represent the if any factor inside the zone of instability would actually activate it. So if the force factor is actually, I think, if it in front of the knee pivot axis, then the knee would not be able to flex. It would not able to flex. Why? Why is that? Because in this case, I think that because since this, even though there's no, it's really pushing along this way, but at the same time, when you have the force factor going this way, it's kind of also counteracting the moment in there. So you're not allowing for a very distinguished moment for unlocking these since they move another way. So I think that would be the reason for that.
Right, so I think you said it somewhere in there. So at the top axis, you need to have ground reaction force vector behind the axis so that it causes an external flexion moment at the top axis in order for the knee to become unstable and to bend. Because if you have it in front, it's a hyperextension moment, and then the knee is stable regardless of what the lock is doing, right? So that's why it's these two conditions that determine the zone of stability: flexion of the top axis and extension of the lock. Okay.
Okay, so maybe we could just do another shorter round, Dr. Ngan.
Yes, just a few minor suggestion points. So first it's a suggestion. So there are many acronyms and abbreviations. So maybe it's having the list of acronyms at the top of the thesis maybe helpful for leaders. And a few minor questions. 6 minute walking test. Is it used straight path or like a rotate?
Yes, we actually did the around the hallway.
So including turning too,
including turning for both.
like turning around at using the same path or turning go to like
It's turning like this. So it would walk in a circle.
or circle.
Because it was because we did it in the hallway of the fourth floor, in which there's like a center block, so there's a hallway going around. So that's where.
Oh, okay. How did you measure the heart rate?
How do I measure the heart rate? So the heart rate was actually being measured by measuring the pulse for 10 seconds, and then we would
You just measured the.
by
Oh.
1 seconds, and that's how we measure.
You mentioned that about the interview. In the interview, so the patient said she was able to perform swimming too. I was so she actually used during this the knee joint during swimming.
Yes.
So-
Yeah, because normally she has to change into her swimming knee,
Okay.
but then when she was wearing it, she just decided to swim with it. Because I told her that a lot of the components were resistant, like that's why. But but we hadn't done an actual test to prove that the knee is water resistant. But since all the components are water resistant, so we kind of told her that, oh, it'll be okay if you would like to do any activities you want with it. So that's why she decides.
So that knee locking mechanism is helpful even in swimming. That's how did you explain that? Why this happened?
Why
she was able to use this in the swimming, although she cannot use her conventional knee, right? What is the point on that? Why is she
I think that one of the components is that for her, the one that she was using, maybe it's not prescribed to her, saying that do not wear it. And at the same time, since there's actually a blue component there where for the extension assist, so maybe you could be afraid that the water may get into there, so affecting the extension assist for that because in the knee that she has, she actually have a line-on string to hold the string for the extension assist. So maybe that will be one of the limiting factors for not being able to. So inside here, where the spring that she has, there's a string pulling it. So that's how.
So the extension mechanism helped, not that knee locking mechanism.
No.
Okay. The last one. So the overall the performance is about similar to the conventional knee, right? So far. Even though like a customer can get some advantage if they choose this knee joint, like for example, if this is cheaper or something, is there any advantage if the performance is same?
Actually, studies have shown that in the AT knee, if we refer to the AT knee, which is the adult knee, and compare the adult knee to the similar like polycentric knee joint design, the AT knee is actually able to offer a greater stem stability in terms of all the low-cost technology, like lower-end technology. Because in the prosthetic knee world, there's the high-end one where it uses the microprocessor and things like that. But when you're looking at purely like a mechanical design, then these ASPL mechanisms are actually able to provide a better performance and offer greater stem stability. So I think that would be one of the selling points. At the same time, as mentioned before, a lot of the knee that we have does not have the damping control and extension assist, in which we are trying to address that and try to incorporate all of those into the knee. So I think that would be also another advantage choosing this knee over the other pediatric.
But in case of AT knees, that performance is better than the other knees, right? That's why
the same classes.
Right. So that's why for the customer there's benefits to choose that. But so far from this result, your knee is same as conventional knee. So in that case, there's no reason for the customer to choose that your knee.
But this is only a pilot design. As I said before, there's more area to be addressed, such as improving the extension assist or improving the axis alignment for better stem piece control. So I think those changes, when we address those changes, might be actually able to improve the performance in the knee, in fact, and then the ultimate goal is actually to have the knee have a better performance in the conventional knee, because if the same performance, then there's no need to design a new knee. Just that, since it's a pilot design, that's why we try to find out what are the area that we need to be addressing in order to have a better product.
I thought this knee may be much cheaper than the high-end knee, so that there's still a benefit for the patient customers to choose this.
I think so, but since I did not do any cost analysis, so I cannot confidently speak to that. But I think that will be the ultimate goal, is to actually produce a low-cost knee where it's still able to provide high functions. But I didn't do cost analysis.
Okay, thank you.
Dr. Krishnan?
Sorry, so no, I don't have any more questions.
You don't have any more questions?
No.
So I wanted to ask you, Calvin, about, so as an engineer, when do you make the decision that you've taken the design as far as you want to go before you commercialize it? So what would you need to do, just in general, general terms, like from where you are now, if you were still on the project, you had to take it to the point, you know, I said to you, I'm gonna pay you until you can get this thing commercialized. So what are the steps that you need to go through? So you get to the point where we get like, and it's on CP24 this morning, where there was a lineup of people wanting to get the new iPhone 6s out there. So, you know, people are gonna be demanding, you know, amputees are gonna be lining up, saying, I want Calvin's knee. This thing, what steps do you need to go through in order to be able to be confident that you've got this to a point where you're gonna be competitive against these other list of needs that are right there?
So, like I addressed before, since first we have to address the problem that we've seen, the design problem, so to make the improvement on the need, and also, and then again, after that, we have to compare it, and then we compare it to the other conventional need, make sure that our needs actually can be able to have a better performance on the patient, on the participant in terms of that. So we, because in order to, so we have to provide a need that is able to, that is able to have a good performance, right? So the second, and also the second thing, if we talk on commercializations, then we have to do the cost analysis to see if this cost of this need and this performance is it related, is it have the competitive edge in compared to the commercial available need. So if it can say if the performance it's comparable, it's kind of like the same as the commercially available need, but then the cost is cheaper, then that give us a competitive edge. But then if we continue to improve it so that it can actually be lower cost and yet have a higher performance, that will be the product that will be demanded. So that will be also the goal that we want to achieve. We have the advantage of both sides.
Okay, that's it for the questions. Did you have any questions? No. Okay, so maybe everybody can